So the next question is question number 17. What it says is that we have to find the number of rectangles excluding squares from a rectangle of size 9 cross 6. So we are given a rectangle of size 9 cross 6 and we have to choose number of rectangles from it excluding the number of squares. So that seems a very nice problem. So let's see how to solve this one.
To solve this problem, let's proceed by making a 9 cross 6 square, 9 cross 6 rectangle.
Okay.
So 9 cross 6 rectangle, basically this question is somewhat different in a way that you don't find these questions like this, many questions like these. So you have to be these are one or two questions, so you have to carefully learn from these questions.
So there's basically not a type of these.
Exactly, you don't find a specific type for these questions, but these questions are important.
So now we are making a 9 cross 6 rectangle. Basically we are dividing it in the squares of size 1 cross 1.
This is what 9 cross 6 rectangle means, that we have 1 2 3 4 5 6 columns and 1 2 3 4 5 6 7 8 9 rows. Now the thing comes, the question says the number of rectangles. So how do we choose the number of rectangles? What are basically rectangles? Rectangle is basically formed when you select two lines from the row portion, let us say these two,
okay,
and you select two lines from the column portion. So this leads to the formation of this rectangle, or you can say square. In this case it's forming square in this case. So to form a rectangle or a square, you need two lines from the rows and one and two lines from the column part. So we count lines 1 2 1 2 3 4 5 6 7 8. We have we have 7 lines in the column space.
So that is a very nice idea, that to count the number of rectangles. We have seen that how a rectangle is formed. A rectangle is formed by choosing two horizontal and two vertical lines, and we are just basically numbering the number of lines so that we can choose two lines from them, or from horizontal lines as well as two lines from vertical line.
So now what is our work? Our work is to select two lines from these 10 and two lines from these 7. So what are the ways to choose two lines from these 10? We have 10 C2 ways, right? And what are the ways of selecting these 2 out of these 7? There are 7 C2 ways, and we multiply because these are independent things. Selecting two lines from these 7 is independent from selecting two lines from these 10, and we multiply them to get the total number of ways of selecting these 4 lines. So now these are the total number of ways to select any geometrical figure of having 4 edges. It may be a square, it may be a rectangle, but we have a constraint. We have a constraint that we have to exclude the squares. So how do we exclude the squares? This is the tricky part. We have found the number of ways to form rectangles or squares, basically a 4-edged geometrical figure,
okay,
but we have to exclude the squares. So we proceed towards subtracting the number of cases we don't want, basically subtracting the number of squares. So our job now is to count the number of squares. So let's proceed to counting the number of squares.
So ultimately we reached to a stage in which we have calculated the number of four-sided figure, and now our job is to calculate the number of squares in a 9 cross 6 rectangle.
Now let's start with the basic square. The basic square is 1 cross 1 square.
Okay.
So how many 1 cross 1 squares are there? There are 9 into 6 squares of 1 cross 1. How do we find them? Let's count. 1, 2, 3, 4, 5, 6. 6 in each row. And how many rows are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 6 1 cross 1 squares in each row, and there are 9 rows. So we can say we have 9 into 6 1 cross 1 squares, squares of dimension 1. So this in the same way we subtract the number of squares which are of the dimension 2 into 2, 2 cross 2. How do we subtract them? Let's count them. This is first 2 cross 2 square, right? The second one will be from 2 to 4.
Okay.
Third one will be from 3 to 5. Fourth one will be from 4 to 6. Fifth one will be from 5 to 7. So for every 2 rows, for every basically okay, let's say we had 5 here, and how many squares we can count in the vertical part?
In a similar idea, 1 will be reduced.
Exactly, but let's make sure for this this part, and then we can follow the same analogy for the rest part, for the rest of the things.
Okay.
So as first was there, first one is here, so second will be here, like from 2 to 4. Third will be from 3 to 5. Fourth will be from 5 to 6. Fifth will be from 5 to 7.
Okay.
Sixth will be from 6 to 8. Seventh will be from 7 to 9. Eighth will be from 8 to 10. So we say that 8 along the column and 5 along the row. So we have to subtract 8 into 5 squares, 2 into 2 squares, which can be formed from 9 into 6 rectangle.
So both 1 is subtracted from rows as well as columns.
Exactly. So as we proceed, when we talk about 3 into 3 squares, we'll be subtracting, we'll be having 7 3 into 3 squares along the column and 4 3 into 3 squares along the row, as we start counting them, like we did in the first and the second part. The same goes for when we say we had when we talk about 4 into 4, then we can say it will be 6 into 3. When we talk about 5 into 5, we can say it is 5 into 2.
So in a similar idea, we have to keep subtracting, but what will be the termination step?
The termination step will be this: when we reach 6 into 1, basically 4 into 1, because we had to decrease 1. So the termination step will be 4 into 1, because because this is the case when the whole 6 into 6 square will be there.
Okay.
And we can form 4 along the column and 1 along the row, and we cannot have a 7 cross 7 square, because there are only 6 columns.
Okay.
So this is the termination step. So we can say that the total number will be 10C2 into 7C2.
That is the total number of rectangles.
Minus 9 into 6. These are not total number of rectangles. Basically, these include the squares also. So these are the total number of 4-edged geometrical figures. Now we are subtracting the number of squares, which are 9 into 6 plus 8 into 5 plus 7 into 4 plus 6 into 3 plus 5 into 2 and plus 4 into 1. This will be our termination step, and thus we get the final answer.
So we have seen that to solve these types of questions, we have to make the figure and we have to count the total number of cases. That is, in this case we counted the total number of four-sided figures, but we have seen that it also included squares, and in the question it is mentioned that we have to exclude the squares. So ultimately our job remains to find the number of squares in the 9x6 grid, and we have seen the method how to find total number of squares in a 9x6 grid, and it can be generalized that if in the question the size were different, then we can also solve it. So we have seen that how to count the number of squares and as well as the number of rectangles in a m cross n grid. So now we'll move to our next question. So now we move to question number 18. It says, if the number of ways of collecting k coupons one by one out of an unlimited number of coupons bearing the letters A, T, M so that they cannot be used to spell the word mat is 93. So we have to find the value of k, and the options are: option A is 3, option B is 5, option C is 7, and option D is none of these. So it's basically we are taking we are taking out coupons one by one, and each coupon bear a letter that is one of A, T, and M, and we are given that the number of ways that we are not able to spell the word mat is 93. So we have to find the value of k. So it seems a very interesting question. Let's see how to proceed this one.
To proceed for the solution to this question, let us see what the scenario is. The scenario is that we are taking out coupons one by one, and let us say we are taking k coupons. Now each coupon has three possibilities. It can be a M, A, or T.
Right.
But there is a constraint that when we draw these k coupons, we should not be able to spell mat, and being not able to spell mat means that we are short of any one of these, M, A, or T. Either I don't have M from these k coupons, or I don't have A, or I don't have T, or I don't have A or T both, or I don't have A or M both. So there are many cases we have to make.
Right.
So let's start making cases. What are the ways in which we cannot spell mat? Let us consider the first case. The first case can be that when I selected k coupons, all of the k coupons were A's.
So in this case we will not be able to spell mat.
Exactly, because we don't have M, or neither we have M nor we have T, so we cannot spell mat. The second case can be when we draw k coupons and all of them are M's. The same case as the first one.
And
also the third thing,
is
similarly
all T's.
We have all T's. So basically here we have three cases in which we cannot spell mat. Now now comes the cases when we say that we have any two of them, like we have M and A but we don't have T, we have T and A, we don't have M, or we have M or T, we don't have A.
Okay.
So in these cases also we cannot spell mat. So let us see the number of ways in which we can have M and A. So basically we are seeing k coupons. So in these k coupons, when we are talking about M and A, we can say that each of the coupon has two options. Either it can be M or it can be A.
Right.
So when I draw these k coupons, each coupon has two possibilities, and drawing of each coupon is independent. So I can say that I can draw these coupons, k coupons, in 2 into 2 into 2 into 2 till k times in these number of ways, so that I get either M or A.
So we get 2 to the power k.
Exactly. We have 2 to the power k ways. But here we have to be careful. We have considered the cases here in which all of them are A's and also in which all of them are M's. But we have already considered these cases above. So we have to subtract these cases. So the total number of ways in which we have M and A both are 2 raised to the power k minus 2. In the same way we can calculate this for T and A, and obviously this will be same, because in this case also every coupon will have two options and we have k coupons, and the selection of each coupon is independent of the other. So we can say that we have 2 into 2 into 2 into 2 k times these number of ways minus 2 obviously for the ones we have already selected.
And similarly for MT we can say that the number of ways are 2 raised to the power k minus 2.
Exactly. So for these two we have the same number of ways. So here we have counted, basically we have manually counted the number of possible ways. So what are the number of possible ways? Total number of possible ways, these will be the 3 we counted before, 3 plus 3 times 2 raised to the power k minus 2, and this total number has been given 93. So we equate it to 93.
Okay.
On solving this equation we can find out that k comes out to be 5,
which matches with the option B.
Yes, it does. It does match with option B.
So can't we do this question in a backward manner, that we find the total number of ways so that we can choose, let us find the total number of ways in which letters A, T and M come over, and then subtract the number of cases which are not required?
Yes, we can do this problem backward, but the problem in solving this question backward is that when we start subtracting the cases that we don't want, they'll be very large in number. So because we can see that the number is the options are quite small, 3, 5, 7, and the numbers we'll be subtracting will be quite large. So there is no point going backward for this question. So we manually add the number of possibilities and then get to the answer.
So we have seen that to do this question we have to consider different case, all cases, so that we are not able to spell the word mat, and we have counted the cases manually. That is, first of all we have counted that we can have all A's, all M's and all T's. So there are 3 possible ways of having these 3 possibilities, and now we count the number of ways in which one is missing out of A, M and T, and we come out that for these the total number of ways is 3 into 2 raised to the power k minus 2, and when we add them and equate it to 93, we get the answer k equals to 5. And we've also seen that solving this in backward will not work, as it will take a large amount of time. So now let's move to the next question. So now we move to question number 19, which is the number of positive integral solutions of the equation x1 into x2 into x3 into x4 into x5 equals to 1050. So we have to find the integer values of x1, x2, x3, x4 and x5 such that they satisfy the equation given here. So let's see how to solve this question.
So for the solution of this question, we see that what the question says is x1 into x2 into x3 into x4 into x5 equal to 1050. What it says is that we have to find the number of positive integral solutions. What it means by number of positive integral solution is we find the values of x1, x2, x3, x4 and x5 such that when they are multiplied they give the number 1050.
Okay.
So basically we have to find the arrangements of x1, x2, x3, x4 and x5. So let's factorize 1050, and it comes out to be 2 into 3 into 5 into 5 into 7.
So this is basically the prime factorization of 1050.
Yes, 2, 3, 5, 5, 7 are the prime factors of 1050. So now let's see for the permutation the arrangements of these numbers into for x1, x2, x3, x4 and x5. So can we say that let's say 2 is x1, 3 is x2, 5 is x3, x4 is also 5, and x5 is 7.
Okay.
So this is one case. It satisfies the equation. The other comes, let's say 3, 2, 7, 5, 5, and thus we see all the arrangements of these numbers 2, 3, 5, 5, 7. But here we have to be careful that we are here, otherwise we'll be missing the cases like 7 into 3 here and 2, 1, 5, 5 here. This also satisfies the equation. But if we only consider the prime factors, the arrangement of the prime factors, we'll miss these cases. And counting these cases, counting each and every case like this is very tedious, because there will be one case when we say 7 into 3 into 5 into 5 into 2 is x1, and rest of them all are 1, 1, 1, 1, 1.
So basically we can include any number of the multiplications in a single group.
Exactly. X1 can be any multiple of these prime factors. So this is very tedious. This is very tedious to do this from this approach. So we have to find some another approach. So we think of a way. Let's say we have x1, x2, x3, x4 and x5 as different groups, as 5 groups.
Okay.
And we have digits 2, 3, 5, 5 and 7. We have 5 digits. Let us say we have to divide 2, 3, 5, 5, 7 in these 5 groups, such that each group gets 0 or more objects. How do we say that? We say that because if we say 2 goes to x1, 3 goes to x2, again 5 goes to x2, we have x2 equal to 15, x3 equal to 5 into 7, let's say 35, and x4 and x5 equal to 5, sorry, equal to 1. This
x3 equals to 35, so
sorry, yes. x3 equal to 35. So this also satisfies our equation.
So basically we have to divide the 5 objects into 5 groups so that each group can contain 0 or more elements.
Exactly. How 0 or more? When in this case x4 and x5 didn't get any number, so we say that they got they got 1, because multiplying any number by 1 we get the same number. So we say that x4 and x5 are equal to 1. So basically we say that we divide these 5 numbers into 5 groups such that each group gets 0 or 1. How do we do that? Let us take 2, 3 and 7 separately, and the alike items 5 and 5 separately.
But why are we doing this?
We'll see, because division of these different objects along into groups is differently done when they are different, and it's differently done when they are alike.
Okay.
So we do it in different parts. Let us take the first part. The first part says that we have to divide 2, 3 and 7, that is 3 objects, in 5 groups, into 5 groups, x1, x2, x3, x4, x5, in such a way that each group gets 0 or 1 object.
So now we are considering the n different objects case.
Yes. What is n different object case? It is basically when we have to divide n different objects into R groups, such that each group gets 0 or more objects.
Okay.
Then the formula comes out to be n raised to the power r.
It's r raised to the power n.
Yes, we did this in the theory. It is not n raised to the power r, it's r raised to the power n. So here we get 5 raised to the power 3. And how does this come 5 raised to the power 3? Let's see. Each digit, let us consider 2. 2 has 5 options. 2 can go to x1, x2, x3, x4 or x5. So 2 has 5 options. Same goes with 3. 3 also has 5 options. It can go to x1, x2, x3, x4 or x5. And the same goes with 7. It also has 5 options. So we have 5 raised to the power 3 ways in which these 3 different objects could be divided into 5 groups such that each gets 0 or more objects. Now we consider the alike items. The alike items are 2 alike items which are 5 and 5. So we consider the formula here. The formula we did in the theory was, if we divide n identical objects into R groups such that each group gets 0 or more objects, the formula is n plus R minus 1 C R minus 1. So the number of ways will be, n is 2 here, R is 5 because we have to divide it in 5 groups, minus 1 C R minus 1, that's 4. So we have 6 C4 ways.
And that comes out to be 15.
Yes. So the total number of ways, in which, basically the total number of solutions for this equation will be 5 raised to the power 3, which comes from the division of n different objects into R groups, and 15 which comes from the division of n identical objects into R groups. That's why we did the different objects differently and identical objects differently, because we have a different formula for them. So this is the total number of solutions for the equation, that is 125 into 15.
And it doesn't match with any of the options from A, B, C. So we have seen that the answer to this question would be none of these.
It doesn't match because 125 into 15, it has to end with 5, and no option ends with 5. So we say that the answer is none of these.
So we have seen that to find the number of solutions such that it satisfies the equations x1 into x2 into x3 into x4 into x5 equals to 1050. First of all, we have tried to done it by counting, but we see that it would be a very tedious job, and we could also get wrong answers, as each group can contains more than contain more than one multiplications. So now we have found a way that we have found two formulas in which we can find the number of ways in which n different objects can be divided into R groups such that each group gets 0 or more objects to be R raised to the power n, and the number of ways in which n identical objects can be divided into R groups such that each group gets 0 or more objects to be n plus R minus 1 C R minus 1. This we have covered in the theory. So, and we have also seen that we can also logically do the first way, that is R raised to the power n. We can also do it by a logical way, so there is no need to remember this formula. So now this is the way to do this question.